Alright, we have section 5.6, the law of cosines. Now the law of cosines comes up whenever we have the specific cases of side, 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 and side, angle, side. Let me get my pen here. So if we have, remember, side, 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 or side, angle, side, we're going to use the law of cosines, as opposed to if we have angle, side, angle, 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 side, or remember the ambiguous case, side, side, angle. Any one of these we would use the law of sines. Alright, so this one we are specifically looking at side, 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 and side, angle, side. Now after this lesson there will come up a section on applications, and that's going to be applications related to law of sines and law of cosines. But this video is specifically just going to be concerning solving triangles of the two cases, side, 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 and side, angle, side. Now we start with a little bit of old stuff. We start with geometry. In geometry and before geometry, you learned that for right triangles, the relationship between the three sides of a right triangle is and always has been and always will be the Pythagorean theorem, c squared equals a squared plus b squared. Now the problem with that theorem is that it only works if it's a right triangle. Alright, we're learning in this particular chapter that trigonometry doesn't have to be restricted to right triangles, so then you might say, well, does the Pythagorean theorem have to be restricted to right triangles? Well, the problem with the Pythagorean theorem is that it's incomplete. This is not everything there is to know about the Pythagorean theorem. This is only a special case of what can really be considered the Pythagorean theorem. So the Pythagorean theorem, in other words, is just a special case. If it's an oblique triangle, in other words, a triangle that's not a right triangle, we just add a little bit extra onto this Pythagorean theorem in order to compensate for the lack of the right angle. And that's this guy. So if I subtract 2ab cosine c, we've now taken the Pythagorean theorem, which only works for right triangles, and we've turned it into the law of cosines, which works for any triangle. This is true for any triangle, whether it's a right triangle or not. This statement is true to relate the three sides as well as one of the angles. Now notice why this still works for the Pythagorean theorem, or for right triangles. For right triangles, angle C is 90 degrees. So if I were to plug in 90 degrees right here, think about your unit circle. What's the cosine of 90 degrees? If you're thinking 0, you'd be correct. So if the cosine of 90 degrees is 0, if it's a right triangle, this whole term disappears. That's what I meant to do. If it's a right triangle, plug in 90 for C, poof, gone. Pythagorean theorem holds true. If it's not a right triangle and it's not 90 degrees, then poof, bring the C back. Alright? So this works for any oblique triangle. Now this is the way it's commonly written, but it really doesn't matter which side is which, because for a right triangle it matters that C be the hypotenuse. But for an oblique triangle, there's no such thing as a hypotenuse. Whether it be A, B, or C all by its lonesome over here, completely irrelevant. All that matters is the pattern. So I see that this is angle C, and this is side C, and this is angle C. I've got side A, side B, I've got side A, side B. Well, if I change this from side C to side B, well then now this is angle B, and these are the other two sides, AC, AC. I could also do it in this format. Side A, angle A. Side B, side C, side B, side C. So really all that matters is the pattern. We've got our basic Pythagorean identity right, or our Pythagorean theorem right here, and then minus 2, whatever the legs, quote unquote legs were, cosine of angle, whatever this was. Now keep in mind, often we're going to be looking for an angle. So if we're looking for an angle, for example, if you're given side, 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 you're going to be looking for all three angles. If you're given side, angle, side, then we're going to be looking for two angles and one of the sides. If we're looking for an angle, sometimes it's easier to rewrite this formula in an alternative form. Alright, watch what I do here. I start with just a generic form of the law of cosines. It doesn't matter which form you start with. And I'm going to go ahead and solve for angle A. And if I'm going to solve for angle A, the first thing I would do is I would take b squared and c squared and subtract them over, just like this. So b squared and c squared now are minus b squared and minus c squared on the left side of the equation. The next thing I would do, in order to get a by itself, I can't get rid of the cosine until I get rid of this whole term right here, negative 2bc. I'm actually going to do this in 2 steps. I'm going to start by getting rid of the negative simply by changing the sign on everything. So this negative becomes a positive. This negative becomes a positive, this negative becomes a positive, this positive becomes a negative. Alright, and when I do that, I'm going to kind of reorder the terms on the left side. Remember, the A became negative, the B became positive, the C became positive, because this side became positive. Alright, that way I don't have to deal with any leading negatives, and it makes it just a little bit prettier. Not a necessary step, but it makes it prettier. Now I can divide by 2bc, so 2bc goes away over here, and it pops up in the denominator on the left side. One more step, get a by itself by simply moving the cosine to the other side as an inverse cosine. So this is a common way to write the formula, although keep in mind it's not necessary. As long as you have the original form of the formula, you can just work through this every single time. Inverse cosine of b squared plus c squared minus a squared over 2bc. So notice the still have the same kind of relationships. I got BC, I got BC. I've got A, I've got A. So if I were to change up if this were going to be angle B or angle C, it just has to match this guy right here, and then the other 2 sides would match here and here. So let's look at an example. Let's see how easy this works out. Alright, so we're doing side, side, side. So I'm going to go ahead and attempt to draw a triangle. Beautiful triangle that's not curved at all. And as always, it doesn't matter how you label it. I'm going to go ahead and label this A, I'll label this B, and I'll label this C. So if this is A, B, C, then side A would be 7, side B would be 24, and side C would be 26. Alright, now notice the things that are missing are the 3 angles, angle A, angle B, angle C. Now, it technically doesn't matter which angle you find first, but now if you remember back to the ambiguous case, when we're looking for the angle, at some point we're going to have to end up taking that inverse cosine right there. So when we have that inverse cosine, keep in mind it wasn't an inverse question to begin with, it was a regular cosine question to begin with. There are going to be 2 possible answers. Now, if we think about this a little bit further, though, cosine has 2 possible answers. Whatever the answer in the first quadrant would be, its second answer would not be in the second quadrant like it is for sine. Its second answer would be in the 4th quadrant, because remember, cosine is positive in 1st and 4th quadrant. So if cosine is positive in 1st and 4th quadrant, 1st quadrant angles go from 0 to 90. 4th quadrant angles, remember, technically go from 270 to 360. We're talking about solving triangles here. Those 4th quadrant angles are too big to fit in a triangle and thus are irrelevant. So when we do our inverse cosine, the calculator is going to give us the 1st quadrant angle, and that's the answer. Now keep in mind, though, it's also possible to have obtuse angles. Alright, it's perfectly fine to have an obtuse angle in a triangle. So when we punch things into the calculator, the inverse trig is either going to give us, for cosine, it's either going to give us an acute angle in the 1st quadrant or an obtuse angle in the 2nd quadrant. All that in short, when we're solving these triangles, the best thing to do is start with the largest angle. Kind of start with the largest angle and work your way down. That way you can kind of keep yourself organized, you know exactly what you're doing, and you can kind of check your answer as you go. If you start with the biggest angle and then you go to the second biggest angle and you go to the smallest angle, and when you get your solutions, all of a sudden maybe the biggest wasn't the biggest, maybe the smallest wasn't the smallest, then you know immediately that you've made a mistake. Alright, remember that the biggest angle is across from the biggest side, the smallest angle is across from the smallest side. So for this one, I'm going to go ahead and start with angle C. So remember, and I'm going to go back to just the original formula. So if I'm looking for angle C, I'm going to start by writing the formula side C, C squared equals A squared plus B squared, minus 2AB, cosine angle C. Remember, angle C is what I'm actually looking for. Now from here I can just go ahead and plug in the numbers. 26 squared equals 7 squared plus 24 squared minus 2 times 7 times 24 cosine C. Now from this point forward, it's kind of up to you exactly how you want to do this. Some people might say it's best to go ahead and square it, multiply that through, and kind of clean it up before you start solving. In my opinion, I don't see the point because I'm really not sure what 26 squared off the top of my head is. I know 7 squared. I'm not really confident with. I think it's 576, but I'm not really completely confident with that. I mean, if they're small numbers, feel free to multiply them in your head. But if you have to grab a calculator, why waste time grabbing a calculator now, solving it, and then grabbing a calculator later? Why not just grab the calculator once? So I'm going to leave it exactly as it's written. I'm not going to simplify anything. I'm just going to go ahead and start solving. So 26 squared. I'm going to subtract 7 squared and 24 squared, just like I did before. And leave this whole guy exactly as is. Now, just like I did before, that negative, I'm going to change that negative to a positive. I'm going to change all these to their opposite sign as well. So that'll be negative 26 squared plus 7 squared plus 24 squared equals 2 times 7 times 24 cosine C. Alright, and then now I'm going to reorder these terms in just a second to get rid of that negative out of the first term. Basically, I'll just move it to the end. But I'll go ahead and move this 2, 7, 24 over to the other side at the same time. In other words, I'm dividing by 2, 7, and 24 all at once. I'm going to do that on this side as well. 2, 7, 24. Alright, so this is all gone. We're left with cosine C equal to that. In other words, we have C equals the inverse cosine of this whole top divided by this whole bottom. And again, I'm going to reorder those terms to make it a little prettier. Need a parenthesis there. Alright, so now this is my answer for angle C. This is technically my exact solution for angle C, but as we've been grown accustomed to doing, I'm going to take this and I'm going to type it into the calculator. Now remember, if you're using a calculator with an older operating system that doesn't have the fraction, the pretty fraction on it, you're going to need to make sure when you type this in, you put an extra set of parentheses around the numerator and an extra set of parentheses around the denominator so that it goes in correctly. Alright, I'm going to pull up my calculator here, and I'm going to type it in to make sure that you're typing it in correctly into yours as well. Now I want inverse. Now before I get started, I'm going to remember that when I'm doing law of sines and law of cosines, I need to make sure I am in the correct mode. When we are doing law of sines and cosines, I'm going to be in degree mode. Let's make sure I put myself into degree mode so that my answers come out correctly. Alright, so I'm going to type second cosine. I want the numerator, so I need to put an extra set of parentheses. Now keep in mind, anything you're good with doing in your head, feel free to do it in your head. For example, 7 squared, I'll go ahead and type 49. Plus, no idea what 24 squared is off the top of my head. Pretty sure it's 576, but I'm not confident, so I won't bother wasting my time to calculate it. Alright, so there's my numerator. Close off the numerator, divide, and now for my denominator. Now 2 times 7, that's just 14, times 24. Close off my denominator, close off the cosine, hit enter, and I get my answer of 98.730 degrees. So 98, let's go ahead and jot that down. So angle C, 98.730 0 degrees. All right. Now notice I said that I was starting with the largest angle, and the fact that I got angle C is 98 degrees means this is definitely going to be the largest angle, because it's not possible to have angle A or angle B to come out larger than 98 because there's only 180 degrees to work with in a triangle. So I know absolutely this makes sense. What I've got here makes sense. Now there's no guarantee that my first angle is always going to be obtuse because there's no requirement that angles always, at least one angle be obtuse. But when I do get my first angle is obtuse, I can feel confident because, of course, I knew my first angle was going to be the largest angle, and this is, in fact, the largest angle no matter what the other two are going to be. So let's go ahead and continue on to figure out angle B and angle A. Now, once I have one angle, if I look back at the triangle for just a second, angle C is roughly 98 degrees. All right. Now you might say to yourself, hey, now that I have angle C and side C, I can use the law of sines to figure out either A or B. And absolutely, you can do that. I personally am not going to. I'm going to go ahead to find my next angle, which I'm going to do angle B next because that's the second largest. I'm going to go ahead and do exactly the same thing I just did right here because I don't see an advantage to switching to law of sines. You might say, well, law of sines was easier. I'm going to say, hogwash, this was just as easy as law of sines, especially since I've technically already got everything filled in where I need it to be in the calculator. All I need to do is change a few numbers around. All right, watch what I'm going to do. So if I move this over here, let's get this out of the way. I'm going to move this over here. We'll just put it over there for now. Okay. Now, notice, to get angle C, remember that this 26 was side C, this was A and B, and of course this was A and B. So 7 and 7's got to match, 24 and 24's got to match. All right, and then of course this was, now keep in mind that's 26 squared. That was angle C. So if I want to figure out angle B, well, keep in mind side B is 24, so I know it's going to be minus 24 squared. And then as far as the 7 and the 26, that's just going to go here and here. So it'll be 7 squared minus 26, plus 26 squared. And then 2 times 7 times 26. So notice, to figure out angle C, this is what I solved for. To figure out angle B, the only thing that's going to change are these two values. They're just going to switch places. And I could have done the exact same thing to figure out angle A. I could have just simply switched the 7 around. So I'm going to go ahead and pull my calculator back up. Hit second enter to go ahead and pull up my previous calculation. And I'm just going to change a few things around. It still says 7 squared, but now it's going to be 26 squared, and the 26 is going to be 24 squared. All right. And of course, this 24 also has to become a 26. All right, so for my second answer, angle B, I get 65.836. Let's go ahead and jot that down. Angle B, 65.836. All right, only have one more angle to figure out. That's angle A. Now I could continue, just hit second enter one more time and switch out my 7 for my 24 because of course I just found angle B, which was across from side 24. So if I were to switch out my 24 with the 7, that would get me angle A, but then I could also realize, hey, there's an easier way. Just subtract from 180. To figure out that third angle, just subtract from 180. I'm just going to subtract the 98 and the 65 from 180. Now, had I been thinking about this earlier, I would have done this to begin with. This angle and this angle, we're going to use those to figure out the third angle. So as you're going along, as you're figuring out these angles, store them in your calculator. So this one I just found was angle B, so I'll go ahead and store that value for B, and then I'll just hit second enter, second enter, second enter 3 times to pull up that original calculation of the 98, and I'll go ahead and store that one for C. Normally I should have done this right after I calculated, but I wasn't thinking. So now I've got both B and C stored in the calculator, so I'll just type 180 minus alpha B minus alpha C to get angle A, which is going to be 15 degrees. And of course, that makes perfect sense because angle A is the smallest angle because it's across from the smallest side. 15 degrees is definitely my smallest angle. So angle A, 15.432 degrees. Pretty straightforward. Alright, here's another one. Solve the triangle with sides 11, 14, and 20. Why don't you go ahead and pause the video here, try it out on your own, and then hit play to see my answer. Alright, let's see if your answer was correct. I'll start with the law of cosines, and what I went ahead and did this time is I rewrote it in the alternative form that solves for the angle, and then I just plugged everything in. A and B are 11 and 14, C is 20, type it in the calculator, 105.633. There's my biggest angle. To figure out angle B, my second biggest angle, I replaced the 20 with the 14, and the 14 with the 20. And I got 42.384. Now, as I'm going along, I stored both of these in the calculator so that to figure out the third angle, angle A, I could just subtract angles B and C, and I got 31.982. Hopefully you got the right answer. If so, let's move on to the next one. Here's another one, 5, 14, 19. I'll stop here or you should pause here for just a second and try it out and then hit play when you're ready. Alright, now you may have been working on this one and started to notice a little problem, or maybe you don't realize that there's a problem, or you may think that you're making a mistake. Let's see what happened on this one. So if you started off the same way you did on the last one, solved for the angle and then plugged things in, when you typed it in your calculator, you may have seen something quite curious. It came out to 180 degrees. You weren't making a mistake. This did, in fact, come out to 180 degrees. Let's think about that for a second. Can you have an angle equal to 180 degrees? If it's a triangle, that ain't possible. Because, of course, if I were not to realize what's going on and I kept going, my next one would come out to 0 degrees. And for that matter, the last angle would be 0 degrees. This doesn't make sense. Now, if you were paying attention to the very beginning, and you remembered a theorem way back from geometry, in geometry, you learned about a theorem that said in order for a triangle to be a triangle, two sides added together have to be bigger than the third side. If not, then it's not a triangle. 5 plus 14 is not bigger than 19. So in other words, this one, when I say solve the triangle, is not possible because it is not a triangle. So just like with side-side angle, we had an ambiguous case. Side, 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 technically, you could think of this one also as an ambiguous case. But there's only two options. It's either going to work or it's not. And what it comes down to is if you have two sides added together are not bigger than the third side, then there's no reason why you should waste your time doing any of this because it's not a triangle. Alright, let's go ahead and move on to the next case, the side angle side case. I give you two sides and an angle. No tricks on this one, no fanciness. Just jump into it. It's going to work every single time as long as you do it correctly. Alright, so we've got our description of our triangle. I'll go ahead and draw the triangle in there. I know that's a perfect triangle. Here's angle A, here's angle B, here's angle C. A is 54, side B is 8, side C is 12. So notice side, angle, side. Now when we have the side, angle, side, we're always going to start by finding that missing side, because once we find that missing side, then this triangle is essentially going to look like a side, side, side triangle, and we can solve just like we did that one. Now to solve for that missing side, we're going to go back to that law of cosines. We're going to set it up to help us find side A. So we'll write it like this. Oops, BC. Cosine A. And we're going to realize something, that if I'm looking for side A, I don't really have to do much manipulation here at all. I just got to get rid of that square. In other words, side A is going to equal the square roots of b squared plus c squared minus 2bc cosine A. So I just got to plug and chug, type in the calculator, and I have my first side. And of course the angle this time is 54 degrees. Alright, just like before, I'll go ahead and pull up my handy dandy calculator, and I just got to type that in exactly as is. Second square root, 8 squared, well that's just 64, plus 144, minus 2 times 8 times 12. I'll go ahead and write 16 times 12 times cosine of 54, parenthesis to close the cosine, parenthesis to close the root. And my answer is going to be 9.754. Let's get my writing utensil again. .754, I believe, was the answer. Alright, so once I've got side A, now I can go ahead and figure out angle B and angle C. I'll figure out angle B just like I did on the side, side, side example, and then I will figure out angle C using, well actually I'm going to keep going in the same order I always like to go in. I'll find the bigger side, or bigger angle first. I'll figure out angle C using the law of cosines like I did on the previous example, and then I'll figure out angle B simply by subtracting 180. So let's do that. Alright, again I was looking for angle C here. So if I'm looking for angle C, I'm going to set it up right here, will be side C. That one's being subtracted. So then 8 squared plus, now keep in mind side A, make sure you store that for A in your calculator, and then I'll just go ahead and use that stored value right here. Keep in mind capital A normally means angle A, but for the purposes of this problem, and since the calculator doesn't do lowercase letters, I'm treating a capital A as side A. On the bottom it'll be 2 times 8 times A. Alright, so to get angle C, I'll go ahead and just type this into the calculator. Let me pull that calculator back up. Alright, 9.754. Again, that was the answer for A. I'll go ahead and store that for A since I forgot to do it earlier. And then I will go ahead and type in my inverse cosine to help me figure out angle C. That'll be 8 squared, which is just 64, plus A squared minus 144. Close the numerator, divide, open the denominator. That's going to be 16 alpha A. Close the denominator, close the cosine. and I have my answer for angle C. So this is my answer for angle C, 84.431. Let's go ahead and store that for angle C. And then the only thing left I have to do is to figure out angle B, which is just going to be 180 minus, keep in mind I'm not going to do what I did before and subtract A and subtract C using the calculator, because remember that A was side A, not angle A. Angle A is just 54 minus angle C, and I get my final answer for angle B of 41.568. So side A was 9.754, angle C was 84.431, angle B 41.568.
All right, now let's look at some applications. There are two specific types of applications I want to look at. I want to look at measuring angles for navigation, and I want to look at area. Now, as far as measuring angles, now up to this point we've measured angles in standard form. In other words, we've measured them such that if I wanted to do a 60-degree angle, we would start measuring at the positive x-axis and we would go counterclockwise as far as desired, in this case 60 degrees. So starting at the positive x-axis, 60 degrees would be slightly less than a full quadrant, which would be 90 degrees. So this is somewhere around a 60-degree angle. Keeping in mind, this is 90, this is 180, 270, all the way back to 360, being equal to, or coterminal to 0 degrees. This is not the only way to measure angles. We call this standard form because this is the most common way to measure angles. All of our formulas that we use are based on angles that are measured in standard position, but we can measure it in any way we want to. Most commonly, when it comes to navigation, we use the compass headings to help us determine our direction, north, south, east, west. Now, whether you hear the word bearing, heading, or course, these all mean basically the same thing. They have to do with navigation. Now, occasionally you'll be given no direction whatsoever. You'll just be told that you have a bearing, a heading, a course of so many degrees. If you're not given a direction, then what you go ahead and do is assume that north is 0 degrees, and then you're going to go clockwise, so that east is 90 degrees, south would be 180 degrees, west would be 270 degrees, and of course back to north 360 degrees. Each direction is 90 degrees apart. So if I say ask for a heading of 60 degrees, well, we can determine a heading of 60 degrees since I'm not given any direction. I assume north to be 0 degrees, and I go clockwise from there. I'm going to go clockwise 60 degrees. Since it's 90 degrees to get to due east, then I know I'm going to be slightly shy of that. So this would be a 60-degree heading. In other words, 60 degrees to the right from due north. Now, this is nice, but it's not helpful when I'm doing all of my mathematical formulas, which are always based on standard position. So anytime I'm giving a heading, a bearing, or a course, I need to convert it to standard position, which really isn't that difficult. If this is 60 degrees right here, then this angle would have to be 30 degrees. Remember that a standard angle is measured from the positive x-axis. So when we're dealing with navigation, that just means we have to figure out where we are in relation to due east. Another way to do it is to give specific directions on the compass. For example, 60 degrees south of east. So instead of just saying a heading of 60 degrees, it says 60 degrees more specifically south of east. We don't assume anything. We are told specifically we are heading south of east. In other words, from east, we are going south. So I'm going to head south from east. So I'm measuring from east and I'm going down from there. So that tells me that this angle right here is 60 degrees, but now I need to convert it to standard position. Remember, standard position starts from positive x-axis, goes around counterclockwise. A couple of different ways I can do this conversion. I can realize that each quadrant represents 90 degrees, 90 degrees, 90 degrees, and of course this angle right here, if this is 60, then this would be 30. Added up, I get 300 degrees. Of course, the quicker way would be to realize that all the way around is 360, and then if I subtract 60, I would also get 300 degrees. Go ahead and give this one a try, a heading of 150 degrees. So if we have a heading of 150 degrees, that means we're starting with due north, and we're going to go clockwise 150 degrees. Well, from north to east is 90 degrees, which leaves me 60 degrees left to go. So 150 degrees would be in the southeast quadrant. Convert that to standard, starting from the positive x-axis, going all the way around, 90, 90, 90. Now remember, if this was 150 degrees, that means this was 90, and this was 60, which really means this is the exact same as the last problem, 300 degrees. Give this one a try, 54 degrees west of north. So if we are 54 degrees west of north, we're in the northwest quadrant, and we are west of north, which means we are measuring to the west from north. So this would be 54 degrees right here. So to convert that to standard, let's go all the way back to the x-axis, tack on an extra 90 degrees to that 54, and we get 144 degrees. 36 degrees north of west. So we are north of west. We are going to the north from west, so we are measuring in this direction. This would be 36 degrees right here. So if we measure back to the positive x-axis, if that's 36 degrees, then this would be 54 degrees. 90 degrees, we are the exact same position we were last time, 144 degrees. Also keep in mind, since we were measuring from west in this direction, we could have started with 180, subtracted the 36, that would have also gotten us 144. Let's apply that to a word problem. Now normally you would be given the picture and then asked to solve from there, but this one I wanted to go ahead and go through the whole process of drawing the picture just for fun. So we have from Tower A forest fire is spotted at 41 degrees west of north. So we have Tower A, we have a forest fire, and it is spotted 41 degrees west of north. In other words, it's not due north, it's 41 degrees west of north. So let's move Tower A off to the side, and then we can draw in our 41 degree angle by drawing in first a north-south line. There's our line of sight, 41 degrees. 41 degrees west of north. Now we also have Tower B, which is 12 miles and 87 degrees west of north of Tower A. So it's 12 miles away, but it's not on a due east-west line. It's 87 degrees west of north. So again, Tower B is going to be slightly to the north of Tower A. So let's move it up a little bit, and we can draw in our 87 degree angle. Now I can keep going. Tower B spots the same fire 15 degrees east of north. So here's Tower B spotting the same fire. Here's my due north line, and I want 15 degrees east of north. And how far is the fire from Tower A? That means we're looking from A to the fire. We're looking for this side right here. Alright, so now here's all the information from the problem, but in order to solve the triangle, I need to know the angles on the inside, not the angles on the outside. So we can work our way around to help us figure out the missing angles, starting with this easy one over here. If the whole thing is 87 and the outside is 41, that means the inside is 46. So we've got 46 degrees on the inside right here. Now let's figure out the angle over here. We can't do the same thing we did over there because we don't know how big this angle is. It's not 90 degrees because this was not an east-west line, but I can use that concept to kind of help myself work around. Let's start by drawing an east-west line from Tower A. If this was 87 degrees, that means this angle right here would be 3 degrees. Now I can do the same thing from Tower B. Let's draw my east-west line. If this was 15 degrees, that means this angle right here would be 75. But there's still a little bit extra down here. To figure out what the extra is, I can realize, hey, I've got a east-west line, another east-west line, and a line connecting east-west line to east-west line. In other words, a transversal. These two angles right here are alternate interior angles. Alternate interior angles are congruent. So if this is 3 degrees, then this angle up here is 3 degrees. So that means 75 and 3 would be a total of 78 degrees. I now have all the information I need. Let's get rid of all the stuff that I don't need. For example, this, and this. Let's just focus on what's important. I realize that this is angle, side, angle, so I can use the law of sines. So why don't you take a moment, use the law of sines to solve the problem. All right, if I'm using the law of sines, that means I need to know angle F. Subtract from 180, I get 56. I can then set up my proportion, x over sine 78, 12 over sine 56. Move the sine 78 over, punch it in the calculator, 14.158 miles. Let's try another. Miami is 1,035 miles from Bermuda. Bermuda is 955 miles from San Juan. San Juan is 1,034 miles from Miami. Solve the Bermuda Triangle. In other words, I know the three sides of the triangle. Let's find the three angle measures. Go ahead and give this one a try. All right, so the first thing we can do is go ahead and fill in the numbers into the picture. And it doesn't matter which angle I want to find first. I went ahead and went with the biggest angle, the San Juan angle. I went ahead and labeled that S, and I set up my law of cosines in order to find the angle. The side opposite angle S would be the 1035, so that gets subtracted. The other two sides would be on the addition and in the denominator. Type it in the calculator. Make sure you type it in correctly. If you're not using parentheses around the entire numerator and parentheses around the entire denominator, it's not going to come out correctly. It should be 62.564. I can do the same thing with the Miami angle, 54.977. And then to get the Bermuda angle, I would just subtract from 180. Make sure you store those two previous numbers in your calculator. I get 62.457. The next stop on our journey would be area. So back in the day in geometry, to find the area of a triangle, you just use that old formula, 1/2 base times height. If you have the base and you have the height, you can find the area of any triangle just by multiplying them and cutting them in half. But if you're not given the base and the height, but instead you're given any two random sides and the angle between, we can manipulate that formula into something else. Now, again, I said any two random sides, so let's say it was this side, and the angle between would be angle A. Now, to find the area, it's still base times height. Base is given, but the height is not. We can solve for the height by realizing that the height itself creates a right triangle that we can then use right triangle trigonometry to solve for the height. I know that the sine of A is h over c, and I know I can multiply both sides by c to solve for the height, and then plug that in. We get our new area formula of 1/2 b for the base, c sine A for the height. In other words, 1/2 bc sine A. And I said it was any two random sides. It didn't matter which two sides as long as this angle was between those two sides. So I could also write it as 1/2 AB sine C or 1/2 AC sine B. As long as you have two sides in the angle between, multiply them, multiply it times the sine of the angle, and cut it in half. For example, 47-degree angle surrounded by a side of length 3 and 8. So I know my area formula is 1/2 AB sine C. So I can just plug and chug. Two sides are 3 and 8, angle is 47, punch it in the calculator, you have your answer. There's really no variation to this, that's pretty much all there is to that, so we're just going to go ahead and move on to the next area formula, Heron's formula. Now, Heron figured out that as long as you had all three sides of the triangle, you could figure out the area from there. You don't need specifically a base and a height, you just need the three sides. You start by finding the semiperimeter. The semiperimeter is when you take the perimeter, a plus b plus c, and cut it in half. Semi means half. And then take that semiperimeter, plug it into this formula. The square root of the semiperimeter times the semiperimeter minus one side, times the semiperimeter minus another side, times the semiperimeter minus the third side. Here's an example. Side lengths 12, 19, 23. Start by finding the semiperimeter. We get 27, and then take that semiperimeter and plug it into the formula. 27 for S, A, B, and C are 12, 19, and 23. From here, we can either plug it into the calculator as is, or we could clean it up, 27 minus 12, 27 minus 19, 27 minus 23, and then type that into the calculator. We should get 113.841. All right, let's try it again. If you are starting to realize that there's a bit of a problem with this one, you would be right. You are not making a mistake. The problem is a mistake. If I were to jump into this and get my semi-perimeter of 22.05 and then plug it into the formula, hopefully you should realize right around here there's a problem. If I subtract, it becomes negative. Negative under a root means imaginary. That makes no sense when I'm asking for the area of a triangle. Area of a triangle cannot be imaginary, so we simply say not possible. Now, of course, we could have avoided all this had we remembered the rule. Two sides, the two smaller sides, have to add to be bigger than the larger side, and in this case, it does not pass that test, and therefore this triangle didn't exist. And I can't find the area of a triangle that doesn't exist, so if you recognize that immediately right off the bat, then you can simply say not possible. Your second clue was the semi-perimeter. If the semi-perimeter is less than that largest side, you can also jump straight to not possible.